Morning, student. Today we are continuing with abstract algebra. Our topic is ring and integer domain. Myself, Dr. Govind Sharma, Assistant Professor, Mathematics. Yesterday we have taken some idea about ideal. Ideal means if subring is called ideal if it is follow the cancellation law. For this, a subset of R is called ideal if it is right ideal and left ideal both. Okay, so ideal have two parts, right ideal and left ideal. Left ideal means if S belongs to S, S is the ideal of R and R belongs to R, then SR. If multiplication with R from right side, then we say that ideal is right ideal, and if the multiplication of R from left side, then we say left ideal. Okay, so we continue. We come to our lecture. Let's start with ideal. Here, and then proper ideal, last ideal. Taken two parts, left ideal and right ideal. Left ideal elements are if like Rs, where R belongs to R and smallest belongs. And right ideal SR, S belongs to S. That means that R multiplies from right side. So we say right ideal. And for the ideal, for the ideal, right ideal equals this is the property of ideal. If subring is called the ideal if it follows cancellation. Or we can say every subring, every ideal is a subring, but every subring is not ideal. Not an ideal. That means the ideal is always ideal is always B. A group of group G. That means R plus is a group and S is a subset of R. So we can say that R plus is the subgroup of group R2. Okay? Now, ideal, there are some remarks. Ideal of a commutative ring is also commutative. Like, like that R are the element of S and S is the element of. But this R is also element of S is subset of R. So this element also belongs to R. Same S belongs to S. S is the smallest subset of S, subset of R. So this is also subset of R. Why these two? Why these two equations? We can take Rf is equal to Sr because R is commutative and S is ideal. So Rf is equal to so okay. So these are the properties. Now so we can say that an ideal always is subring. An ideal is a subgroup of group R and a commutative ring. The ideal of a commutative ring is also commutative. Now, now there are some definition of proper and improper. Let every every ring R has two improper ideals, which is R itself and identity element. It's called null identity. Any other ideal of R except that every ring R has two improper ideals, which is R itself and 0. These two ideals are called improper ideals. Okay? Or remaining ideal is called proper ideal. Those two ideals, which called proper proper. Okay? It's called proper ideal. Ring, a ring has no ideal, it's called simple ring. If a ring has no proper ideal, it's called simple. Actually, the statement is want to say that a, a ring has two ideal always, which are improper ideal. Means ring itself and zero. Zero is the null ideal. But इसके अलावा except of these two ideal are called proper ideal. Okay, proper ideal. And a ring have no proper ideal is called simple. A ring no proper ideal is called simple. Now theorem. Consider the set S1, S2, R matrix. R matrix. A 0, 0, A B 0, 0, A B 0, 0, and R ring of what element then and so number one S1 and S4 are right ideal, but not equal. Second, S2 is left ideal, but not right ideal. Third, S3 is neither left nor nor consider the sets S1, S2, S3, S4 are matrix. S1 is AB 0 0, S2 is AB 0 0, S3 is A0 0 B, and S4 is 0 A 0 B. And R is a ring of all 2 by 2 matrix. Actually, this question is giving us that R be a ring of matrix ring, then there are some subset of S1 is this type, S2 is this type, but AB are integer. Then we have to show that S1 and S4 are right ideal, but not left. And S2 is left ideal, but not right ideal. And S3 is neither left or nor right ideal. So we start. In all conditions, we see that first condition of ideal that A minus B belongs to S is satisfied. So proof we will discuss only on second condition. It is clear that condition 1 for that is EB belongs to S1, S2, S3, implies A minus B belongs to S1, S2, S3. That is S1, S2, S3, S4 are subgroup of R. The condition the condition factor is S R belongs to S for R belongs to and for all S1 belongs to for right hand. And R has to for left hand. Taken S1 is equal to AB 0 0 belongs to S1 and R belongs to ring, so R we take CD. That means S1R AB 0 0 CD is equal to AC plus BA C plus BE AB E. That means S1 is right. This multiplied by this AC BE AB. This has become 0. This is 1. So we can say we can write it directly 0. This becomes AC plus BE AB 0. This is belongs. So so S1 is Actually, we take the element F1 A B 00 and R C D E F, then multiply this S1 R. This is also the element of S1 type. So S1 belongs with AC plus B is always an integer. This is come as integer value and CB is a integer value. So the product of this also integer value and this is belong to S1. Now belong to S1. So we can say that S1 is again again RS1. Now we will show that F1 is not left ideal. So we multiply R from left side C D A B called is multiplied by so E A E B. So yes, this C C C B A. This is not a S1 type element. So this is not belong to S1. So because S1 has the element like A, B, 0, 0. Their second row is 0. But here all row R1 and R2 both are not 0. So this is not element of S1. So this is not an element of S1. So we can say RS1 is not an this is not an element. Now third is similarly we can see S2 is a left side but not right but not right. S3 AB 0 belongs to S and R CD. So S2R AB 0 CD is equal to we can say AC AD BE and B. This is not belongs to belongs to. So so S3 is not an right. So this way we can see that S3 is not right ideal. Now we will show that S3 is not a left ideal also. For that we take R multiplication with left side. So we take R S3 CD here A0 this by this AC BD answer AE. So it's not element of S. So we can say so RS3 is not an element of S because S3 element is A0 0 bit है. But this is not a belongs to S3. The diagonal element only exists in S3. So, we can conclude that S3 is not left ideal and we hear the question that consider the set S1, S2, S3, S4. We will have to show that S1 and S4 are right ideal, S2 is left ideal. Okay. For that, we know that the matrix multiplication is not commutative. So here we take R from R and S1 element is A, B, 0, 0 type. R is CD here. We for the right ideal we multiply from right side. R is in right side. So when we multiply with this, we find AC plus B, CB. Okay. So this is the belongs to S1. So we can say that it is right ideal. But RS1, when we have to prove, we will see that it is left ideal. For multiplication with R from left side, we found this type of element. There is no second row is not zero. So this is not element of S1. So we can say this is not a left ideal. Similarly, we can prove for S2 also. Now we take the case of S3, where we have to show that S3 is not a right ideal or left ideal. So we take element from R, T, D, E, F, multiply by this. This is not element of F3 and not element of F3. And similarly, when we multiply from left side, this is also not element for F3. So we can say this is not a left element. Yeah. Alright, so this is not a F3 is, so F3 is. Now student, we come to the quiz. Now student, we come to the quiz. Now student, come to the quiz. Which is the ring in integral domain? Then we know that Q plus and Z plus. Yesterday I told you that Q plus and Z plus are the integral domain. So N plus is not a ring, 2Z plus is not a commutative ring with unity, so Q plus is a integral domain. Which is true? CR is an integral domain. This is the I told you yesterday that this is the incomplete sentence. CRU. If here add U, commutative ring with unity is an integral domain. Then CR is an integral domain. This is the wrong statement. AB is equal to BA with CR. This is the right because commutative ring always follow the commutative law. This statement is not true. To Z plus is integral domain, Z plus B integral domain, Z plus is a field. So 2Z plus is an integral domain. This is the wrong. Which statement is true? N plus is a CR is no because this is not a ring. The ring has zero divisor. Q plus is a field. Q plus is a definitely field. So this is the right. So student, this is the topic of our ideal ring and integral domain. Now we will discuss about maximal ideal and ring from other topic of ring that principal ideal domain and maximal ideal. Okay. Thank you very much.